In this video, I want to talk about limits, specifically the limit of a function. So we could say the limit as x approaches a. So a is some specific value along the x-axis of some function x. All right, and we say that the limit as x approaches a of this function x equals L. That would be the limit if we can get as close to L as we want by choosing values of x that are closer and closer to a. All right, so that's kind of the technical definition, just that we can get closer and closer to that point. So this is a y value. This is a y value, and then here's our x value. Our x value is approaching a, and as we get closer and closer to a on the x-axis, the y values approach L. So this is all kind of very general right now, so let's look at a specific example. I want to look at the example of taking the limit as x approaches 2 of x squared and say, what does that equal? What does this function seem to approach? What value does the function approach as x gets closer and closer to 2? So let's look at this graphically. All right, I just want to look in the first quadrant. All right, so we're going to have what? 1, 1, and then 2, 1, 2, 3. That puts us at 4, right? 1. Okay, so we're going to have something, our function is going to look something like this, right? Okay, so that should be the point. Not quite, it should go right through here, but you get the idea. And on the other side, obviously, it'll look something like this. Okay, so the idea here is as we get, I'm going to use a different color just to emphasize this here. So this part, the x approaches a, just means that we're letting the x values get closer and closer to 2. And we can do that, we should do that both from the left side and from the right side. Those are called one-sided limits. We'll talk about those more in the next lecture. But that is what we mean, is we're letting the x values get closer and closer to 2. And then what's going on with the y values? So we can see as x gets closer and closer to 2, the y values are going up this way, right? Or from the other side, they're coming down. All right? So what we're looking at specifically is, when we're coming in from both sides, do the y values seem to converge to a certain point? That's the idea here. So I've not drawn this to scale. So right here, that should be 4. So we'll just call that 4, and we'll squeeze in a 2 and a 3 here, right? Okay, but the point is, you can see that as we get closer and closer, as x gets closer to 2 from both sides, the function values, the y values, they want to go to 4, all right? So we would say the limit of this function is 4. We could also make a table, right? So if we made a table, x and y, and we could take, 1.9 or 1.99 or 1.999 on this side, or 2.1 or 2.01, 2.001. Now, if we used our calculator, we could see what these y values would be, and we would see that as x gets closer and closer to 2, and this is from the left-hand side over here, this is from the right-hand side. As we go from here, we're getting closer and closer to 2. We would see over here that these going from, like I said, from here to here, these would be getting closer to 4. From here to here, these would be getting closer to 4 as we get closer and closer to 2. All right? So that is what the limit means. The issue that I want to address now, though, is that notice in this case that if f, let's put it over here. So if we say f of x is x squared, notice that f of 2 is 2 squared, which is 4. Here's the thing, this is the subtlety that I think students struggle with. The function value has nothing to do with the limit. These are two completely, the fact that they're the same in this case is a coincidence. all right? At least conceptually, it's a coincidence. The limit really has nothing to do with the function value. There are a special class of functions for which the limit and the function value are the same, and they're called continuous, but in general, the limit is not the same. So just because they happen to have the same value, don't get them confused, because that is the temptation for most students, is that they want to say that the limit is the function value, and if the function value doesn't exist, then the limit doesn't exist. And so I want to look at another example for which that's not true, okay? So we're going to actually look at a very similar function to the one that we just looked at. I'm going to call it g of x. And I'm going to say that g of x equals x squared, but I'm going to restrict this domain. It's only going to be x squared when x is not equal to 2. Otherwise, we say I'm not going to assign a value at all to g of x. So what is g of x going to look like? All right, well, let's see if I can do a little bit better this time. 1, 2, 3, 4. Let's start with putting this. So there is a hole right here, okay? Because g of x is not defined when x equals 2. It's only defined when x is not equal to 2. So we end up with something that looks a lot like x squared, and we want to go through that point there, right? So, and it's symmetric, so it comes back up. All right? So this looks a lot like x squared, except it has this hole here. It's not defined. G of 2, there is no g of 2. There's no y value associated with x equals 2. All right? Now, the question is, what is the limit as x approaches 2 of g of x? All right? Well, once again, we're looking at as we approach from the left and from the right, what do the function values do? Well, we see that these head up this way, coming from out here. They're coming from larger values coming down. And if you look like right along right along here, they converge to 4. All right? So that's what they're converging on. Even though that part is not part of the function. All right? It's not actually a function value. The function values seem to want to go to 4, even though it's not there, even though it's missing. That's what they converge to. So we would say that the limit of this function is 4, even though g of 2 does not exist. That's my shorthand for does not exist. All right? So that's one way we see that the limit could still exist even though there is no function value. I'm going to give you one more example using a similar function. I'm going to call it h of x, and this is going to be piecewise defined. So what I'm going to do is I'm going to say h of x is x squared when x does not equal 2, and I don't know, let's just call it 0 when x does equal 2. All right? So now h of 2 is defined, right? H of 2 is 0. That's precisely what that means. H of 2 is defined, so this function is defined at x equals 2. So let's take a look at the graph of this. All right, so again, 1, 2, 1, 2, 3, 4. Let's put this point up. So again, we have a hole here. We'll talk about that in a second. But we have a hole here, and the function value at x equals 2, the function value is actually down here. Okay, so once again, we know we need to go through this point, so we have something that looks like this, and it comes back up the other side. Okay, so again, so in this case, we're looking at x equals 2. Well, I guess I can label these, right? Here's 1, here's 2. We approach from the left, we approach 2, we approach 2 from the right, and once again, function values are approaching this point right here, right? So the same thing is happening in all three of these cases. The function values on either side of x equals 2, those y values are converging on that point right there, which we know 1, 2, 3, 4 is y equals 4. That's where they're converging to. The fact that the function value is 0 has nothing to do with the limit. So we say that the limit as x approaches 2 of h of x is 4. because that's where the function wants to go as we get closer and closer to 2. Again, we could make a table of values, and if you picked, like we did in this first one, if you pick these, notice for all three of these functions, you pick these values, and these y values would get closer and closer to 4. All right, because we're not looking at what's happening right at 2. What happens right at 2 varies in all three of these situations. In this case, right at 2, the function equals 4. In this case, right at 2, the function doesn't exist. And in this case, right at 2, the function value is 0. But nonetheless, in all three cases, we have that the limit is the same. All right? So this is just to kind of highlight what the limit is. All right? So just to quickly summarize then, we have three possibilities. One, the limit, if we go back to our original definition here, the limit as x approaches a of f of x equals L. And recall we said that means that we can get the y values as close and close to L as we want just by taking x closer and closer to A. So this L, it could equal f of A. All right, so that's this first case. In this case, the limit was 4 and the function value was 4. All right, so that's what we have here. It could be, secondly, that f of A does not exist, but L does. All right? In other words, we can still have the limit even if the function value doesn't exist. That's what we had here. Limit exists, it's 4, function value doesn't exist. And then finally, the one that we're looking at here, f of A exists, L exists, but they're not the same. All right? Okay, so that's just to kind of give you an example of what a limit is and how it's defined and the fact that it doesn't depend on the function value at the point.